Albert, are you there? Hi, good afternoon, everyone. So this week we will work on geometry problems. We will see quite a few similarity problems, which generally suggest that we have some proportional reasoning to make. So similarity is a very important concept in geometry. It usually requires you to have fundamental understanding about the ratios, proportions, and so on. But geometry does not just treat that. It's more about you have an inherent feeling about geometric figures that look quote unquote similar, right? So, but at middle school level, you will mostly work with similar triangles. And we will see there are certain important concepts in terms of proportions, like first dimensional, second dimensional, and third dimensional. When you have 3D figures in space that look similar, what does that mean? Okay, if we have time, we may look at AMC 10B and 12B problem from last week, just a few days ago. We'll see whether we have time, okay? Okay, first problem. This is number 6 from mini number 30. So basically you have a square here, WXYZ, and for this square, you know M is the midpoint of YZ, the base side here. And then, so you connect X with M, then draw a perpendicular at M to this XM. So this line will intersect WZ at A and intersect the extension of XY at B. So from that, you can see that it looks like this is a kind of just a no, not equilateral, it's an isosceles triangle. Looks like AXA kind of just equals to XB. But that's not the point. You were asked to calculate AZ here. Okay, so what is your thought when you see a figure like this? Well, in general, we don't advertise that you want to memorize certain tricks or rules about anything in math. It's far more important you understand all the underlying principles, ideas. So rather than memorizing a certain rule, you have to understand why a certain rule or trick works. However, there are some problems that are so basic and you see them so frequent that almost you just kind of reflectively should know what you are going to do. Okay. In this case, because you have a square, which is nice, you have 4 congruent angles, or right angles, 4 congruent sides. Then you have another perpendicular XM, AM or AB. They are perpendicular, and that foot of that perpendicular M is actually on the side of this square. So what are we getting here? You immediately get a lot of similar triangles. Can you see why? Well, let's talk about this. When you have a square or rectangle, let's forget about top part. Let's just think about it. If you have right angle, you have right angle here. And somewhere on this baseline, you have a point. From there, you get somehow a right angle. So this is right angle. Now, do you see similar triangles? Yes. Immediately, if you say this is A, this is B, this is C, then D is E. So triangle ABC is similar to triangle ABC, CDE. And why is that? Because this angle is complementary to this angle because they have a right angle in between, right? So angle ACB plus angle ECD equals to 90 degrees immediately. And that means that this angle must be congruent to this angle. So you have one more pair of congruent angles for two right triangles. Therefore, the two triangles are similar. Well, this is kind of very standard, very basic fact when you deal with a figure like this. Okay? If we have time, we'll see AMCB, 10B, and 12B problem later today, but we may not have time. But I want you just recognize this fundamental fact whenever you have a figure containing something like this. This is almost like your instinct. When you see something like this, you know you get a pair of similar triangles. Okay? But it's not a good idea to memorize this as a trick. You should, if anything, you should memorize the fact that why they're similar. It's because this right angle in between and with this point on the line, which by itself is a straight angle, 180 degrees, it cut the line or the straight angle into three parts. One right angle in between, so the other two must be complementary to each other, meaning they sum up to 90 degrees. And because we have two square corners here, two right angles, then you immediately get a pair of similar triangles. So that's the point here. So we can see that triangle AZM is similar to MYX, right? Just exactly because of what we just discussed about. So that the ratio between AZ to ZM is the same as the ratio between MY to YX, right? Because they are similar, two triangles are similar. So AZ over ZM is the same as MY over YX. And what is MY over YX? We already know M is the midpoint of YZ, so that ratio is just 1/2. Therefore, AZ to ZM is also 1/2, but MZ is also by itself is 1/2 of the side length of the square, so AZ is just a quarter of the side length. That's about it. How do we know the side length? There's a condition here. The area of this square is 144, therefore you should immediately see the side length is 12, because 12 squared is 144. For those of you who really want to do math competition in the future, I took a look at the recent AMC Mathcount problems. More and more, I'm convinced that those competitions are really about speed and accuracy. You are truly under very stressful situation where you have to work out everything very fast. And better yet, you better take the kind of just a shortcut approach for every problem. Take the best approach. A lot of problems are solvable, but it takes extra minutes. Then you cannot perform well in those math competitions. How do you get faster? Well, more practice, doing more problems is certainly important, but you need to be very solid in fundamental things like 12 squared is 144. That should be really consuming 0 seconds in your brain. You immediately see 144 is the area of a square, side as 12. That's just a reaction, okay? If you cannot do that, you won't go very far in American math competition because the entry levels like Mathcounts, AMC, they all require you to be very, very fast, okay? So that's this problem. We won't write the detail because this problem is kind of easy. Well, easy if you have practiced enough geometry problem, knowing the trick we just talked about, okay? But if you never really study the trick, you have to reason it out on the spot, which means it takes more time. But if you have to do it, then you somehow you think about it. AZ, what do we need to get AZ? AZ has to be somehow connect with the rest of the figure. And what is the first candidate that is somehow associated with AZ? Must be this triangle AZM, right? This is the first thing that AZ can play a role in something. So you start investigating the triangle AZM. From there, you should be able to independently discover this similar relationship. By the way, triangle AZM is actually congruent to BYM. And that's easy to prove because ZM equals to YM. M is the midpoint. So therefore, it can be easily shown that those two triangles are congruent. Anyway, so much for this problem. Let's move on to the next problem. Okay, in this rectangle, ABCD, AB is 6. That's the height. The measure of angle DBC is 30 degrees. That's super nice. You almost immediately know everything about this figure, right? Because now you immediately have a 30, 60, 90 triangle in this DBC scene. Because triangle BDC apparently it's a right triangle, it's a 1/2 of the rectangle. Then you have a 30 degree angle there, DBC. So you know almost everything. Now M is the midpoint of AD, and then CM, DM, they intersect at K. So what is the length of MK? This is another standard trick that you should, just like 12 square is 144. When you have something like this, you also should immediately see a pair of similar triangles. And what is that? Well, if you don't know, you can still reason it out. Just like in the previous problem, the reasoning goes like below. What is the length of segment MK? MK has to be somehow connect with the rest of the problem. And what is the first thing you think about the MK? Well, MK is part of a triangle, right? And that triangle is MKD. Now you see a triangle MKD there, and we need to figure out MK, and we know a lot of things about this overarching figure is a rectangle, M is the midpoint, and you have another 30, 60. But in terms of MK and this triangle MKD, what is the easiest and the closest thing connected with it? It must be another triangle that is actually similar to it, that is CBK. And the standard trick is something like this. Let's just say you have a trapezoid or anything that gives you a pair of parallel lines. Okay? Whenever you got something like you connect the two diagonal, you immediately get a pair of similar triangles. And that came from the fact that in the trapezoid, the base and the top, the two lines are parallel to each other. And we know parallel lines generate a lot of congruent angles. Therefore, this angle is congruent to this angle, and this angle is congruent to this angle. Of course, the other pair, their vertical angles, of course, they are congruent. So immediately you get a pair of similar triangles. Again, we don't want to memorize a trick like this. So, oh, I have a trapezoid, I connect diagonals, I get a pair. No, we don't want to memorize that fact. What we do want to memorize is that when you have parallel lines, they tend to generate congruent angles. And for a particular setup like this, you connect the two diagonals. The parallel lines will give you all the needed congruent angles. But if you memorize this fact, so in the general problem, say we only give you two parallel lines and then intersect that. It's not a trapezoid, but it still gets same properties. So you don't want to memorize a specific case. You want to memorize the principle. Okay, so in this problem, if we need to know MK and we recognize that there's a pair of similar triangles here, how can we connect with the rest of things? Well, for this type of problem, it's actually very straightforward because once you know they are similar, we know all the ratios, right? The similarity, there's a ratio, like say, what is the ratio between MK and the CK? That's the same thing as the ratio between DK and the BK. And so if we know the total length of CM, and we know this ratio, we can easily figure out. But do we know CM? Yes, of course we do. We know the whole thing already because this is a rectangle. AB is 6. Therefore, BC is 6 times square root of 3 because this 30, 60, 90 triangle thing, to make it clear, because AB is known, so BC is also known due to the fact that we know this is a 30, 60, 90 triangle. The three sides are in the proportion 1 to square root of 3. That's the two legs, and the hypotenuse is 2. So BC is the longer leg. That's square root of 3 times whatever base the shorter angle side is. That's a 6. Now how do we know CM? Well, once we know the total length of BC, we know it's half DM here. DM, because M is a midpoint, so DM measures at 3 times square root of 3. Then by the Pythagoras theorem, we should be able to compute CM. Okay? To make it just clear, we just want to quickly write down something here. So because AB equals to 6, because triangle BCD is a 30, 60, 90 triangle. Therefore, we get this longer side, BC equals to 6 times square root of 3. Therefore, DM, of course, I jump a few steps, but just to save time and space, you should be able to fill in the gap. So I jump a little bit. So from here to here, you need to say M is the midpoint of AD, and AD is congruent to BC, and so on. But I skip those points, just make sure that you understand. So we know DM. Therefore, by the Pythagoras theorem, what is CM? CM equals to square root of this side, CD, which is 6 square, plus this DM square, 3 square, 3 square, which is 27, right? So this is 36 plus 27. So this is 3 times square root of 7, because this adds up to 63. You factor out the 9, and that's 7. So we know CM. Why do we need to know this? Because you want to figure out what kind of fraction MK is of CM. To that, we just need to know the ratio. But the ratio is very easy to see. It's just 1 to 2, right? Because DM is 1/2 of BC. M is the midpoint of AD. AD is congruent to BC. So MD to BC is 1 to 2. Therefore, MK to CK is 1 to 2 as well. So that means that MK is just 1/3 of the total of MK and CK, right? This is 1 to 2, the total is 3. So the ratio between MK and MC is 1 to 3. But we just figure out MC is right here. Therefore, MK equals to square root of 7. Of course, this is a kind of just simplified just a procedure because I skip a few steps, but you should be able to fill that up. And the takeaway of this problem is that when you have a parallel line, a pair of parallel lines, you intersect the two, trisect it in way like this, two cross, then you immediately get a pair of similar triangles right here. That's so frequently examined, and in fact, those just patterns appear in real life problem as well. So to get this point, you have to recognize something like this quite fast. When you see some problem like this, not, of course, you recognize this fact doesn't mean that fact will be helpful for your specific problem, but for simpler math competition problems like this, usually that's perhaps the only or one of 2 or 3 test points that you are being examined. Okay, so that's that. Very important. So now we see 2 different similar triangles generated. One is that we divide a straight line into 3 angles where there's a 90-degree angles in between, then the rest 2 must be complementary to each other. And in this case, where you have a parallel line, we trisect the parallel lines in a way like this. You also get a pair of similar triangles. Okay? All right. Number 9, number 30. So in this diagram, ABCD is an isosceles trapezoid. So my son asked me what is isosceles trapezoid. Well, this isosceles word really means just the two sides are congruent, right? So you have a trapezoid. In general, trapezoid, you have a pair of parallels, the top and the bottom. The other two sides, in general, they're kind of just arbitrary. They can be in any unspecified number, but if the trapezoid is isosceles, then that means that the two sides, AD and BC, must be congruent. That also means that we have a trapezoid, so that angle A must be congruent with angle B. You can argue, well, if I have a trapezoid, these two sides are congruent, but it doesn't have to be in this way, right? It can be in this way. That is also congruent. But if that's the case, you have a parallelogram. You see that? This is a parallelogram. It's not a trapezoid. We don't consider a parallelogram to be trapezoid. So essentially, when you have an isosceles trapezoid, essentially you have a parallelogram, but flip this side, the missing part of this triangle, outward. So that's why this is actually an isosceles triangle, but the whole figure is an isosceles trapezoid. Okay, so this problem says that AB is shorter, right? So midpoint of AB is P. Then you draw two parallels, PQ parallel to the left-hand side AD, and PR parallel to the other side BC. And not surprisingly, those two lines, PQ and PR, will intersect this diagonal BD at 2 point XY. And you are provided with a whole bunch of numbers. CD equals to 8, AB equals to 6. That means the top is 6, the bottom is 8. But what is the ratio between PX and YR? Okay, that is interesting. PQ and YR. Let's think about this problem. So we have a trapezoid. We know the top is 6 and the bottom is 8. So the top is shorter. Of course, I'm not drawing it perfectly in terms of exact numbers, so not just to proportion. Okay, so you have this, and then you have intersections like this. I believe this is called X, this is Y. Now, we want to know, what is the other one? Oh, QR. Okay, QR. This is A, B, C, D. So we want to know the ratio PX and YR, I believe. Upon the first look, this looks scary, right? PX and YR, they are not connected at all. How can we figure out a relationship between PX and YR? Let's highlight those two line segments here. Those two, and they are not even connected. And they're in an awkward position. Looks like it's not easy to connect with them. But first thing in geometry is that when you have a problem, you look really close at the things that you are being asked to prove or solve, and make sure that you identify the relevant quantities, how they're connected with the rest of the diagram or the figure. So PX and YR, how do we get PX? Well, PX is the X. P is the midpoint of AB. X is the intersection of this PQ scene and BD scene. Similarly, Y is the PR with this BD scene. Okay, so that means that we got to cut off this BD by PX and the PY. But if you see that, you should immediately see, not maybe immediately, but very soon, you see that PX and the YR are connected to both PQ and PR, right? At this point, you are supposed to have reasonable good geometrical intuition. We have not just arbitrary trapezoid, we have isosceles trapezoid. That means that AD congruent to BC, but PQ and PR are parallel to them respectively. So therefore, we got two parallelograms on the left and the right. So PQ equals to AD equals to BC, but that also equals to PR, right? So essentially triangle PQR is an isosceles triangle. You just shifted the AD and the BC into those two line segments, PQ and PR. Essentially, that's what it is. If that's the case, we figure out a way to connect PX to YR in the sense that we don't really need to compute this ratio directly, at least not. What we can compute is, can we figure out an easier problem? First, what is the ratio between Px and Py? Because naturally, you would be surprised if you are asked to solve this ratio Px and Yr. They are not somehow kind of symmetrical to each other. At least there's no apparent connection. But if you recognize that Py is something you really want, at least more desirable, right? Because Px and Py are in a similar situation. They are both connected with P and the two intersection points Px, Py. So can we figure out Px, Py first, then translate that into Px and Yr? That is doable because Py and Yr add up to PR. And PR equals to PQ. Essentially, it's something like this. If you know what kind of fraction Px is of PQ, if you can figure this out, everything will be solved, right? Because if you can figure that out, you can similarly figure out what is Py over PR. But the PQ and the PR are congruent. So that means that in terms of fraction, we are talking about the same denominator here. So if we know this ratio and we know this ratio, we will be able to figure out the ratio between Px and Py. Because the bottom PQ, PR, they are the same. Once we know this one ratio, the YR over PR can also be figured out because just one minus the other fraction, right? Because Py plus YR is just PR. So if we know the proportion Py over PR, we will immediately see that 1 minus this must be YR over PR. And that will give you the desired ratio between Px and the Pyr. Is everybody still with me? Essentially, this is just kind of fraction work. You need to know the fraction, the ratio. So if you know the ratio between Px and the PQ, then similarly, must be similarly, you will know Py and the PR. And from that point, everything will be solved. That's how you perform analysis. So essentially, we reduce a pretty hard problem to a much easier problem. Can we figure out Px over PQ here? This is the one, it's red. This is the one we want to figure out. Because once, if we can do this, we will be able to crack down the whole thing. So what is Px over PQ? This is a problem we just did a while ago, right? Not a while ago, short time ago. That's essentially this problem. See? In any mathematical problem, when you face a tougher problem, can be somehow connected with the easier problem that you already solved. That's exactly this problem. Oh, well, not exactly, almost exactly. This is the thing. We have parallel lines because this is rectangle. We cut two kind of cross cutting transecting lines here, and then they intersect the K. We get a pair of similar triangles. Therefore, we know the ratio between MK to CK, that's 1 to 2. From there, we know the fraction MK of the total length of MK and CK, that's just 1/3. That's exactly what will happen here. The trick is that you recognize the pair of similar triangles we need. And what is that? It's this one, right? Just because of the way it did not appear that obvious, you should recognize that that's essentially the same thing there. And this is not just kind of, for this particular one at least, not just similar, they're actually congruent. Did you see that? Because here DQ equals to AP, because this is APQD is a parallelogram. You have two pairs of parallel lines, AP parallel DQ, PQ parallel to AD, but you can get this kind of feeling if you draw the figure correctly. You can immediately tell. Therefore, DQ equal to AB, AP, not AB, I'm sorry, AP, but that also equals to BP, right? So the yellow highlighted triangles are not just similar, they're actually congruent, but from that point we know PX over PQ is just 1 to 2. So check, we have done this. Got first result. But how about the other one? What is PY? What's the fraction of PY to PR? Well, now the same idea, it's just the numbers are slightly different. Well, for this one, we also have a pair of similar triangles, but you have to be careful. This time is this little triangle and this big triangle, right? Because that's how you get the fraction of PY of PR. For this one, we don't have congruence, but that's okay. All we need is similarity. How do we know this? We already know this is 3, right? So what is this? This is A minus 3. Remember, the bottom is 8, and this portion, RC, is the same as PB is 3. Therefore, DQ equals to DC minus CR. That is A minus 3 equals to 5. Therefore, the ratio between, one-dimensional ratio between those two similar triangles is 3 to 5. That means that PY to YR equals to 3 to 5. Right? And therefore, remember YR is actually what we want, but hold on to that, not just right now. So essentially, PY to PR is 3 to 8, the total. So you can also, at this time, you can take a shorter cut. You just say YR is 5 over 8. YR over PQ is 5 over 8. Right? That's what you want. So therefore, you're almost there. You need to figure out the ratio between PX and YR. We can get that ratio from a common denominator because PQ is the total, like I said, 8 here, not numerical 8, but 8 parts. So YR equals to 5/8 of PQ, and the PX is just 1/2 of PQ, right? Remember, PQ and the P are the same. So therefore, the ratio between PX and the YR is just 1/2 over 5/8. That's 4/5. Okay, because this guy is just 1/2 of it. This guy in the bottom is 5/8 of it. That's slightly bigger. So the ratio is 4/5. This problem is pretty interesting. Essentially, we use the same earlier result twice to figure out PX and PY. But once you figure out PY, you can get a YR. That's it. Nothing really just significantly tougher, but you do need to recognize that how to make it, the connection. Yeah, just like Steve Jobs says, how do you connect dots in life? How do we connect the dots in geometry? So PX and YR, they are somehow connected through this PY thing. Okay, but PY is in a similar situation as PX, while PY and YR, they add up to PR. That's how you see the connection between PX and YR. Okay, next problem. How many problems do we have? 1, 2, 3, 4. Yeah, this is okay. This is an important problem. Looks like we are proceeding a little bit slower than I wanted, but that's okay. Yeah, you have a frustum. What is a frustum? You have a cone, or write a cone here. You cut off the top. Then you get the bottom, the remaining part is called a frustum, which weird name, but it is what it is. So find the formula for the volume of the remaining part. First of all, you need to know a few very important things, right? What is the formula of a cone? If you don't know that, now you should know. It's 1/3 of the area of the base times the height. Or maybe use little capital H, but it doesn't matter. This formula not just applies to the volume of the cone, but also any pyramid. If you ever learn calculus, you will see immediately why this is the case. It doesn't matter what kind of you think about a cone is a special prism which has infinitely many sides on the base, right? You have some standard, should I diagram that? Yeah, this one. You have, this one should be not dotted line. If you have a pyramid like this, you have a triangular base. Still, the volume is the same formula. You know the base area, you have the height from the other vertex to the bottom, to a perpendicular, that's the height. Whatever shape you have, or the base doesn't have the triangle, it could be, say, a hexagon, right? A hexagon, something like that. So that gives you a hexagon. Whatever kind of pyramid you have, the volume formula is always 1/3 times the area base area, and height. So the important thing is this 1/3 coefficient, because you don't really have a cylinder or a prism. You have a cone or prism. There's only one vertex at the top which connect to every vertex on the base. Because of this shape, you have to take a 1/3, make it smaller. Okay, that's so much for the volume of a cone. Now, we cut off the top of a cone. What does that mean? It really means one thing. The thing that you cut off, that is missing here, which is smaller cone, is similar to the original cone. This is just very similar on the two-dimensional plane. Let's say we have a triangle here. if we cut off the triangle with a line parallel to the base, cut off here, what do we have? We have this cut off top, a smaller triangle, and that is similar to the original triangle. Why? Because we have a parallel line here. Almost exactly the same idea. Now we, instead of have parallel line, we have a parallel plane. Parallel to what? To the base plane, right? So that's how you cut it off. You have a parallel plane cutting off the top. So the one that was cut off is a similar cone to the original cone. That gives you the clue of how to do this. How do we know the remaining frost term? Well, the frost term volume is the difference between the big cone, the original cone, and the smaller cone, which is the one that is missing, right? And we do know the formula. So here we know the radius of the top circle, which is the intersection circle between that cutting parallel plane to the cone. We know the radius of that smaller circle, and we know the radius of the top, the bottom bigger circle, and we know the height, the remaining portion of the cone called the frustum, the height of that frustum. So what do we need? We still need one thing, that is the missing height of the smaller cone, which is denoted as x here. So we do not know x, but we know the other three. But can we figure out what x is? Because once we know x, we will be able to both calculate the volume of the smaller cone, which would be 1/3 pi r squared. That's the area of the base times this x. If x is the height of the smaller cone, right? You see that. But what is the volume of the bigger original cone? That must be 1/3 pi s squared. That's the radius of the bottom circle or disk. The height must be h plus x, right? X is the one that was cut off. H is the remaining residual height. So they add up to the original height of this one. Okay, we know those two. Now if we figure them out, you just subtract the top, that's the cutoff cone from the original cone. That must be the formula for the volume, the frost term. So this must be pi times a squared times h plus x minus r squared x. So this is the volume of the frost term is expressed by this. The only thing that is not known is, of course, x. We don't know what is that height. But do you see any way to figure out? That's why this similarity is so important. Because the smaller cone is similar to the original cone. So that means that everything corresponding to the other must be in the same proportion. Anything. So the height x to x plus h. This is, remember, this is the height of the smaller cone. And x plus h is the height of the original bigger cone. The ratio between those two must be exactly the same as all the other relevant corresponding quantities, and that all equals to the one-dimensional similarity ratio. When we're talking about two similar figures, whether it's 3D or 2D, there's a ratio, right? That's measured in one-dimensional. And what is that ratio? The ratio is already given to you. It's just the radius of the smaller cone's base. The ratio between that one and the radius of the larger cone's base. That's S. So this must be R to S. Did you see that? This is nothing but the similarity ratio between the two figures. and measured in one dimension case. The radius. The two radii are in this proportion relationship. Therefore, that's the same thing as this. So now you can solve this equation easily, right? You just do cross product. So you got Rx plus Rh equals to Sx. And we group everything about x on the left-hand side typically. So we got R minus x. And so s is bigger, so we better write s to x. That gives us the right one. So this will give us Rh. Essentially, you move Rx to the right and then swap the two sides. You get that. That's the basic. So this tells us that x equals to Rh times, oops, sorry, this is R, not x. So x equals to Rh times s minus r. So you plug in this one into the formula we see. Now you get the formula. Of course, there will be some simplification there. We won't do. We don't have time. But essentially, this is how you solve a problem. You based on similarity, you solve this equation right here, and get x. Now you get x. You can plug in into the volume formula. Okay. So once again, similarity, proportional reasoning, all that very important. Okay, do I need to solve this? Well, now you have seen quite a few problems. You know, this is once again, you have a trapezoid, AB parallel CD. So the area of triangle PAB is A squared, and the area of a PCD is B squared. That really, it's interesting. A and B are positive. Explain why the area of the whole area must be A plus B squared. Looks like a lot of algebra involved. Indeed, there's algebra involved here. And you can see that we can reason everything out straightforward way. Okay, so because triangle PAB is similar to triangle PCD, right? We have already learned that. Just, you know, the trapezoid, the two diagonals intersect, giving you a pair of similar triangles. But the area ratio is A squared over B squared. That means that since we don't know the exact value of AB and CD, we only know the area of PAB is A squared. PAB is A squared, and triangle PCD is B squared. So that, if you have really good intuition, this is immediately tells you the similarity ratio between the two similar triangles. Why? Because the areas ratio, area is a two-dimensional thing, right? Areas ratio must be the square of the one-dimensional similarity ratio. Does anybody understand what I'm talking about here? We have a pair of similar triangles. Then we have a one-dimensional, essentially a fraction ratio, right? It could be, say, the ratio between this side and this side, or this side to this side. It doesn't matter. Or you can say it's this side to this side. Regardless, this is a one-dimensional ratio. Actually, anything correspondingly matching within the two triangles must be in such a ratio as well. For example, everybody knows the incenter or circumcenter of the triangle. Incenter is when you have three angle bisectors, they meet at a point, and this is called incenter. Similarly, you will have the incenter of the big triangle. Now, if I ask, what is the ratio between this line segment and this line segment? That must be exactly the same as the original ratio we talked about. Because the two triangles are similar in every way. So anything you find in both, they must match this. And this can be rigorously proved, and the proof is not that hard. So once we know the area of this PAB and the PCD, we immediately see the areas ratio is A squared over B squared. Therefore, the two-dimensional thing, which is areas ratio, is this thing. The one-dimensional ratio must be A over B, right? That means that although we don't know what AB and CD is, we do know AB over CD is A over B. Okay? So from that point, if you really want to calculate, explain the area of ABCD, you can do in several ways, but one of the way is the hard way. You just say, without knowing what ABCD is, you just compute this, just using algebra, right? You assume the height is h. But because you know this fractional ratio, you will know the 3h as well. You know this h. You just say if this is h, then this must be, according to this is h1, that's the h1, h2. h1 over h2 must be A over B, right? And the total must be A plus B over A times h1. That's the whole total height. This is very straightforward. So basically, you can assume a few algebra, then do it. The trapezoid's area is just AB plus CD times this h divided by 2. Then you can ultimately show, after some algebraic manipulation, you will be able to show the area must be this. It's very straightforward. It's a little bit tedious. We will not do it here. We just get the idea for doing this. Essentially, it still comes from the fact that we have similar triangles, PAB and PCD, and everything else can be done by algebra, okay? So if the area of PAB is this much, this is much. But there's another way to do this. Let's just use similarity proportional reasoning argument. Is if you look at this, if you know the ratio is already A and B, A over B, right? You know the similarity ratios here. And this is very common in terms of doing triangles area. Let's take a look. Once we know this ratio A over B is the one-dimensional similarity ratio between the two triangles, everything else can be reasoned out. For example, what is the area of this triangle? How do we know anything about it? We already know the top triangle is A squared. That was given to us, right? This is A squared. So therefore, this ratio, the green one to this top yellow one, the area must be the ratio between these, because they share the same height, right? If you turn it a little bit, this is the base of the green circle, and this is the base of the top yellow circle. But we do know this fraction is A over B. Therefore, because those two triangles share the same height, the areas ratio must be the ratio between the two bases. So therefore, the green triangle's area must be A squared times B over A. That's the ratio between the two bases. And this is its own area. So this gives you AB. Okay? Similarly, we know this must be AB as well. This one, I should not do it that way. Let's use a different color, blue. So this blue one is in the same situation as the green one, so this must be also AB. Now for the total area, it's just A squared plus AB, the green one, plus another AB, the blue one, and plus B squared, which is the yellow bottom triangle. And you can immediately see this is A plus B squared. So this is much faster than if you do the algebraic hard way. I look at last week's AMC problems. Quite a few problems actually require you to do it much faster in this way. Not the way, say, I set up complicated algebra H1, H2, and at the end you make a long kind of road, then get to a simple fact like this. You can do it that way, but that's very time consuming. But it is the orthodox way of doing maths. Okay, you stick with the definition of the trapezoid area, top plus bottom times height divided by 2. You go that way, it will work. It just doesn't work in the math competition like AMC if you do that. Okay, that's very unfortunate, but you are expected to do something really quick as this one. Okay, all right, we are at this time. We don't have any time, but we still have a problem to cover. I just urge you to read the solution. It's not that hard. After today, you see that so many similar triangles can be formulated once you have a parallel line here, and that's almost exactly here. The only trick for this problem is that you need to connect the dots. Literally connect this vertex of the square and this vertex of the triangle because they are on the same line. Anyway, so that way you will see that you will be able to calculate this shaded area. Okay? So as promised, we take a very quick look of this year, actually last week, a few days ago, AMC 10B and 12B. This problem is number 16 in B, in 10, and 13 in 12, meaning that it's an average problem, not the easiest, but definitely not the most difficult. 16 is a fairly good number in 10, meaning it's relatively more difficult. And 13 in 12, that's just right in the middle, right? 25 problem. So you have a rectangle here, and you put a square somehow, just rotate it so that one of the vertex on the top edge of the rectangle and one vertex here is connect just at the bottom of the rectangle, and another one is on the side. And we were told that this rectangle is a 4 by 8, so the height is already marked for you is 4. Therefore, the bottom is 8 here, and the square has side as a 5. It just makes a weird overlapping with the rectangle to create a shade like this. So what is the area of shade? Well, if you recall our first problem of today, you'll be able to see that's exactly how it works. By doing this, you create a lot of similar triangles. Okay, you see that? If we just consider it carefully, this is say 4 by 8. Then you have 5 here. How did I do it? Yeah. So it drew it that way. Not perfect square, but that's what it is. Excuse me. So, how do we solve this problem? We want to look at the area of this shaded area. Okay. In the old-fashioned way, you can think about the shaded area in this one in terms of 2 approaches. You can think about this is the ultimate total this smaller rectangle containing this one. This is total area. Then you subtract this triangle, subtract this triangle, and subtract this triangle to get the area of the shaded area. This is doable. Actually, when I tried this, I immediately jumped to this solution and overlooked another better and quicker way is to think about, instead of subtracting those three angles from the rectangle, you can subtract this angle, a triangle, from the square itself, right? Essentially, very similar things. You subtract something from a total, but if you choose this second one, subtracting this pink triangle from the square, it will be much faster than you subtract the three triangles from the rectangle. Okay? Apparently, one is much, much better. And unfortunately, when I did this problem, it took me a lot of time because at my age, I'm an older man, my kind of just stuck with just an old-fashioned orthodox way. But either way, you have to do the same thing. That is figure out the area of those triangles. In the former case, you need to figure out three. In the latter case, you just need to figure out one. That's why it's much more preferable. How do you do that? You already know all those triangles are similar, don't you? Don't you? Remember what we discussed today? This angle is complementary to this angle. Therefore, this angle is congruent to this angle. So, and similarly here, even if for this tiny one, it's exactly the same thing because this is a right angle. So all those three triangles are similar. How about the pink one? Actually, that's also similar because once we know those three smaller ones similar, notice that this one is just has a vertex angle to this smallest first triangle. So this must be also similar. Okay? So let's stay with the easier one. You can do the more challenging one if you want to have some fun, but at this time we think that's not worthwhile because essentially we'll get the same result anyway. So how do we know this? Well, we still have to argue that this one is similar to this one, right? Because we know this one. So simply because we know this one, this is the height is 4. The hypotenuse of this is 5. Therefore, this is 3. Everybody get it? This is 3. But similarly, this one is similar to this one. So this is 3. This is 5. How about this one? Well, now this is this leg to this leg. This is a 5. This must be 5 times 3/4 because that's the ratio between this one and this one, right? So the shorter leg to the longer leg is 3 to 4. Therefore, here the longer leg is 5. The shorter leg must be this one. And once you know this, you immediately see how to do the area, right? Because this is much quicker. 5 times this is what? This is 15 over 4. Yeah, just write it that way. This is the answer of this one. So that's much quicker. So this problem, it's not that difficult, but it's already ranked at number 16 in AMC 10. And even for 12, it's still 13, right in the middle. So from this point now, you should feel a lot of confidence about those geometry problems. Let me tell you one thing. AMC up to 12, the geometry problems are relatively easy to some group of people and very difficult to other group of people. What is the former and what is the latter? The former is the group of people who study authentic proof-based geometry. That will really force you to think deeper and harder into many geometry problems. On the surface, you have AMC, Mathcounts. All those problems are actually fairly kind of just easy, okay? that's it for this. Next week, Thanksgiving week, we won't have any class. Okay, so after Thanksgiving week, we will resume. See you. Bye.